This might suggest that the so-called imaginary time is really the real time. And that what we call real time is just a figment of our imaginations. In real time, hello Sinmiedo. Hello Excito. Hello Sinmiedo. How are you? In real time, the universe has a beginning and an end at singularities that form a boundary to space-time and at which the laws of science break down. So in the real time, the universe has a beginning, which is the Big Bang. And if it were to have an end, it would be the Big Crunch, maybe. And those are singularities. And this is where science kind of breaks down at these singularities. But in imaginary time, there are no singularities or boundaries. So maybe what we call imaginary time is really more basic. And what we call real is just an idea that we invent to help us describe what we think the universe is like. But according to the approach I described in chapter 1, that is Stephen Hawking, scientific theory is just a mathematical model we make to describe our observations. It exists only in our minds. So it is meaningless to ask which is real or imaginary. Hello, Andre. Hi, Stephen. Hello, Sinmiedo. Hello, everybody. Thank you so much for being here. Can we get 10 likes? Can we? So which is real or imaginary time? It is simply a matter of which is the more useful description. One can also use the sum over histories along with the no boundary proposal to find which properties of the universe are likely to occur together. For example, one can calculate the probability that the universe is expanding at nearly the same rate in all different directions at a time when the density of the universe has its present value. In the simplified models that have been examined so far, this probability turns out to be high. That is, the proposed no boundary condition leads to the prediction that it is extremely probable that the present rate of expansion of the universe is almost the same in each direction. This is consistent with the observations of the microwave background radiation, which show that it has almost exactly the same intensity in any direction. So as we know, the cosmic microwave background radiation temperature has been measured for almost, I believe it's been a while, like a couple of decades worth of measurements and whatnot. And we keep finding that it's about the same average temperature no matter which direction you do this measurement in and which direction you look, pretty much. If the universe were expanding faster in some directions than in others, the intensity of the radiation in those directions would be reduced by an additional redshift. So if the universe had an expansion which was different in a certain direction, for example, faster in a particular direction than some other particular direction, then we would see a difference in the CMB temperature in that direction, okay? It would, the intensity of the radiation in those directions would be reduced by an additional redshift because that part of the universe has receded more, is accelerating away more than other parts of the universe, if this were to happen. Further predictions of the no boundary condition are currently being worked out. So this whole like boundary thing, like, is there really a boundary? Or is the universe kind of flat, infinite, and sort of expanding in every direction in sort of the same way, you know? So a particularly interesting problem is the size of the small departures from uniform density in the early universe that caused the formation first of the galaxies, then of the stars, and finally of us. So that's the other thing, is that there are small perturbations to the smooth universe. These are called higher order perturbations of the smooth universe, or little overdensities in the smooth universe where things are not quite as uniform as when we say uniform, right? Not perfectly uniform. There are some higher order perturbations to the uniformness or the homogeneity. So, but those little perturbations away from totally smooth, basically roughness or overdensities, is how we got the galaxies and the stars and ultimately us, because of course we're